Math 2414, improper integrals, some limits to expect. Needless to say, we're going to be taking quite a few limits. Basic limit strategy is stick the number in and hope nothing goes wrong. But by the very nature of our improper integrals, things are going to go wrong and we need to know how to get a handle on them. These are not all the limits that we're going to run across, but there are going to be some common ones, and I just wanted to not just give you these limits, but remind you, just pull the door shut, just remind you how to come up with some of these limits with the correct visual aid. Some of these make sense. For example, number one, the limit is x approaches infinity of x to the nth power. I'll break it down into two categories, if the n is positive or if the n is negative. And by the way, if the n is 0, this is equal to 1, so the limit's just 1. If my n is positive and I let the x get larger and larger, then I'm just raising a bigger and bigger number to a positive power, and it's just going to keep getting larger and larger and larger. This limit is infinity. However, if my n is less than 0, then that means this is a negative exponent which reciprocates it. In other words, it turns it into one of these. So maybe we should go and answer number 2 before we go back to number 1 and finish the second half of this. Number 2, the limit is x approaches positive or negative infinity of 1 over x to the n power if that power is positive. If you have a positive exponent in the denominator. This one's easy. In a fraction, if the denominator gets larger and larger, infinitely large, while the numerator is static, in this case it's just 1, then your fraction collapses down to 0. Which is, by the way, the other part of this limit up here. Because up here, if our exponent is negative, then a negative exponent would reciprocate into a positive exponent, and then it would collapse to 0. For the rest of these, I'm going to use some graphs to help us remember how to do these. I do expect you to know certain graphs. For example, the graph of f of x equals e to the x. Starts out hugging the x-axis on the left side as an asymptote, crosses at 1 because e to the 0 power is 1, and it skyrockets to infinity. If you remember the graph of f of x equals e to the x looks like this, then each arrow on either end actually tells you a limit. This left arrow, the arrow on the right basically says, as x approaches infinity, e to the x approaches infinity. Well, y approaches infinity, but y is just another name for f of x, and in this problem that's e to the x. So, the limit as x approaches infinity of e to the x is actually infinity. And I meant to write these in red so they would stand out. We'll fix that real quick. But the left end of this graph says, as x approaches negative infinity, as the graph goes forever to the left, y is actually approaching 0 because you're asymptotically approaching the x-axis. And so the limit as x approaches negative infinity of e to the x is 0. You could also argue this one, similar to this one, that you could turn into a fraction whose denominator is getting larger and whose numerator is static. For number 5, I just need to look at the graph of e to the negative x. Well, the graph of e to the negative x is just the graph of e to the x reflected across the y-axis. F of x equals e to the negative x would start high and then flatten out to the right. So, the arrow on the right says, as x approaches infinity, e to the negative x approaches 0, which means the limit for number 5 is 0. But the arrow on the left says, as x approaches negative infinity, as the graph goes forever to the right, e to the negative x approaches positive infinity because the graph goes up forever. So if you know the graphs of e to the x and e to the negative x, those limits are easy to recover. The next two, as you can tell, involve the graph of natural log, and you'll notice that I didn't take the limit to negative infinity here. If you remember the graph of natural log, you'll remember y. And if you don't remember the graph of natural log, well, here it is. Being the inverse function of e to the x is just the reflection of that graph across the diagonal line, y equals x. And if all that college algebra speak went over your head too fast, let me know and I'll hook you up with my college algebra videos about inverse functions. I'm going to get this coordinate plane drawn where I want it in just a second. F of x equals the natural log of x is only on the right side of the x-axis, starts out plummeting straight down, well not straight down, crosses the x-axis at 1 because the natural log of 1 is 0, and then slowly but steadily makes an increase as it moves to the right. This right arrow says, as x approaches infinity, as the graph goes forever to the right, the natural log of x approaches infinity at a very slow pace, but it will go up forever, which means that limit number 7 is infinity. But this graph has a vertical asymptote on the y-axis, and so the left end of the graph says, as x approaches 0 from the right, remember that little plus means coming in from the right side of a number, then the natural log of x, the y value here is plummeting downwards to negative infinity. And if you can just picture the graph, it's easy to recall these. Speaking of graphs, we actually are going to run across some limits involving arctangent. And you may be wondering, where would that come from? Well, if you recall on our work with trig substitutions, we had we had some integrals that transformed into 1 over x squared plus a squared, and the antiderivative of that was an arctangent. And so we're going to be running across those again, so it would be helpful to know what the graph of arctangent looks like. And I'll admit, this is a graph that not many people remember off the top of their head. So I'm just going to show it to you, and if you want more details, get with me, and I'll explain why it's this graph. In short, you take the graph of tangent, the one graph in the middle that's trapped between two asymptotes, reflected across the diagonal line, and you get something that looks like this. The graph of arctangent is kind of interesting because it actually has two different horizontal asymptotes. Rational functions can only have one, but tangent's not a rational function. It starts out, and by the way, these two horizontal asymptotes are at negative pi over 2 and pi over 2. The graph of arctangent on the left starts off on the bottom horizontal asymptote, curves up and hits the origin, and then it does the same thing up here as it approaches the upper horizontal asymptote. This arrow on the right says, as x approaches infinity, as the graph goes forever to the right, arctangent of x, the y-coordinate, is approaching pi over 2, because it's getting closer and closer to this horizontal asymptote. And similarly, this arrow on the left end of the graph says, as x approaches negative infinity, as our graph goes forever to the left, the y-coordinate, which is measuring arctangent, is approaching this other horizontal asymptote of negative pi over 2. If you don't know the graph of arctangent, it might be difficult to recover these. There are ways to do it using definitions of tangent and right triangles and which trig functions are positive and which quadrants and all that jazz. But at the very minimum, I would memorize them, but more than that, I would understand that they come from this graph. And if you want more details about this graph, let me know. I'll tell you everything you want to know. Are these the only limits you need to know? Nope. But we're going to run across these guys quite a bit. Also, L'Hopital's rule. Not going to review it right now, but as it pops up in examples, I'll review it then.